My name is Stuart Denman, and I'm the founder and technical director of Surreal Software. Today I'm going to be talking about continuous worlds and streaming game resources from slow media like DVD and CD. This is my first GDC talk, and I forgot to take my shot of vodka, so if I seem a little nervous, then that's why. Ooh, can't blow it. So the first thing I'm going to do is introduce the concept of streaming, what it is, why you'd want to stream in your game, and talk a little bit about the development impact of introducing a system like this into your project. Then I'm going to introduce what I call resource streaming, which is where you stream all your game resources, textures, models, sounds, everything, not just traditional audio and video, into your game as the player plays. Then I'm going to talk about Surreal's implementation of this in our Riot engine, and I'm also going to discuss Sony Europe's The Getaway, which was just released, and Naughty Dog's Jak and Daxter. And then I'm going to get into problems and solutions that we've run into and other developers have run into implementing a system like this, which includes issues with prefetching data, making sure it's there when you need it, DVD performance issues, and memory fragmentation and other problems related to memory management. So what is streaming? Well, it's the act or the operation of crossing a stream or river, preferably on a fallen log or perhaps a bridge of some sort. No. This is sort of my definition of what streaming is, and there's really just two simple requirements. One is that the data is loaded only when it's needed, and that it's a background operation. So that means it doesn't stall the game or interrupt the player at any time. And fortunately, all current modern hardware and PCs and so on can do this without interrupting the gameplay or any CPU, so your AI and your rendering can continue without being affected at all by the loading process. So why stream? Well, you can generally have larger and more detailed levels, and by detailed, it kind of depends on whether you have a big open environment where there's a lot of level of detail and stuff, or there's a game that's inside a room and it's closer up, where there's a lot of details that you can see up close. It means also that you can have more unique content, and in a lot of ways that contributes to the detail and the look of the level. And then the memory only contains the most active content. Some things I think is very important, that you don't have a lot of memory that's being used for things that you're not going to see for another 2 minutes in the game. And it allows you to have continuous levels, which is kind of a very popular thing in some very popular games like Grand Theft Auto and so on, where you have very big worlds that you can drive around in and experience without any type of loading or stall between the areas. And it really gets the player into the game, and they believe that they're in a living, breathing world and not just a series of connected levels. Since you only ever need the data that's active at any one time or is being used by the renderer or the game engine, your initial loading time is very small, because you just need to load what you're going to be seeing right at the beginning and not the entire level. And generally, since the loading system is dependent on when the data is needed in the game and when the engine requires the data, your engine can be much more versatile, because it's built or it utilizes the data in a very specific way instead of loading everything that is potentially going to be required. You're only loading the things that you need right then. So you can really distribute by incorporating level of detail technologies in with this system. You can distribute the loading in any way that you like, either by loading the details that you see up close or by loading things that are far away in a more open landscape environment. And then it really gets around a lot of current console limitations like memory restrictions and DVD performance problems like slow DVD. And of course, a moose is a good explanation of why you should use streaming. So the development impact on the system, or on integrating a system, affects the whole team, not just the programmers. The size and scope of the levels are highly affected by this. So you can do a lot more with streaming. You can have a lot more unique content, and that means the designers can build their levels a lot larger. And also the way that they build the levels, especially in a continuous world, is going to be a lot different because you can't necessarily fit this whole world into Maya and edit it efficiently or something like that, or your custom level editor. So how you design that and how you lay out your levels is very much impacted by this kind of a system. And then the location and distribution of the encounters that the player comes into as they go through the game is also really affected by it, because you're limited in what you can store in memory for any one area. And the designers need to be able to distribute these in such a way that it can load the next encounter as the player moves between encounters. And there has to be enough time in between those encounters to load the data for the next area. And as I said before, the artists and sound designers and anybody that makes content really is affected by this, because the unique content that they build can be much, much greater than in a normal engine, because it doesn't all have to be in memory at once. And then the amount of detail that they can store, that's just the kind of quality that they can put into all the content too. It can be much, much greater, again, because you can stream it as you go. So on programmers, the data handling requires a lot of thought. You can't just go in and get a pointer to a texture or a model and just start mucking with it or start reading it. You have to make sure that the data is actually valid and has been loaded before you start using it. I'll get a lot more into that later. And then adapting an existing engine to the system requires a lot of work, again, for the same reason. You can't assume that the data that you're accessing is valid. And you have to check for that, and you have to handle if it's not there as appropriate. And then on your testing team, they have to be looking for cases, again, where if they move through a level too fast, the data might not be able to load in time, and they need to look for that, know the signs and symptoms, and report those problems. So first I'd like to talk about audio and video streaming that everyone, I'm sure, is used to and is almost required for any modern console game. So you essentially have a stream of data stored linearly, usually in time, on the DVD. And you allocate a large buffer in memory, and you load in the first bit of data from the DVD. Once the data is finished loading, you can then start playing it in memory. And then you initiate a second buffer load that occurs for the next block in the stream. And then usually for this system to work, the buffer that's being played has to take a lot longer to play than it takes to load. If you don't do that, you get like skipping and popping. That's what happens on your car stereo if you don't have a good buffer on it. And then again, once the play has completed, the load is also completed, and you can swap the roles of the buffer and load the next piece of data. So to demonstrate this, I'd like this half of the room to scream and then swap with that half of the room, and then we'll repeat the process. I'm just kidding. Every time I laugh, it makes a weird noise. All right, so extending that further to textures and geometry, where instead of streaming, buffers of audio, we're going to try and stream areas of the game in. This is used a lot in racing games, so I'm going to use the example of a racetrack to extend this. So you can see with the racetrack there, I've broken it up into segments of about a half mile. And you can see from any one segment, you can never see another segment of the same color. So I've got to alternate red and purple. And that's really important, because it means you only need to have those two buffers in memory at once of And each segment of track, then I'm saying for this example, has all the textures and geometry that you'll need for that segment. So if I do have half-mile segments, then at 100 miles an hour, that gives us 18 seconds to load the next segment, which is a lot of time. If everything was optimal on the PS2, you could load about 80 to 100 megabytes of data in that amount of time, which is a lot. So if the artist were to build 100 megabytes of content for that area, they'd be working for about a month, though. So generally, that's pretty prohibitive. And in normal operations, with other stuff going on and processing the data and so on, you wouldn't get nearly that rate. It would probably be about a third of that time. So, like I said, if the artists were to build that much content, it would take them a long time, so you never do that. You usually have trees and cars and things like that, or shared or repeated resources that you reuse throughout the track. And of course, textures you reuse everywhere. I mean, the road textures are repeated and everywhere. So these types of data can't be handled the same way as a track. They have to be shared and kept separate from the unique resources in a way so that they can be managed differently. So what I would say is, why not treat all resources separately? So if you can treat each resource independently, then you can determine when to load that resource so that it can be used, and when it's no longer needed, you can flush it out, and so on. So it's kind of two different approaches, is treating your unique content one way and your shared content or your reused content another way. And then the other approach is to treat everything as if it was shared, so you kind of just bring it in and reuse it and figure out how often it's used. Now, if you do that, the loading becomes much less predictable, because, like I said before, the data is loaded as it's needed by the engine. So if you have reusable content that repeats itself throughout the level, you can't really predict very well how that data is going to be used and where it's going to be used. It all depends on where the designer and the artist place it within the game. So the way this would look in a completely unoptimized diagram is that you have your data now is stored in more of a database form and less of a linear stream. And so the data then is loaded in the order that it's requested by the engine, which again is for all intents and purposes random. So you'll end up with an order that's much less predictable, and the worst part about this is that your read head would end up skipping around, and I'm sure, as all you know, seeking on the DVD is very slow. And then in memory, instead of having this sort of simple double buffered type thing, you now have places where you store the resources in memory, and that has its own set of problems that it entails. So once the data has loaded, then the engine is free to use it in it however it needs. So what kinds of resources can you stream in? Well, when you write a general purpose streaming system, you can stream pretty much anything, and things you might not expect, like code. If you have a scripting language, it can be streamed in. Controller vibration data, even tiny little things like localized text and lighting things can be read in. And then the system is also able to do traditional streaming, like video and sound and stuff like that. Those aren't the kind of resources you would want to load in all at once. You'd want to bring them in with smaller data requests. So there really isn't much stuff that you can't stream. Pretty much the only kind of data that you can't stream is, of course, procedural stuff. Any kind of resource that you may take and modify, store in memory. And of course, you need some way to initiate this whole process, and that has to do with like a scene graph or some kind of visibility information or connectivity information that tells the engine what to load next and how to use it. So now I'm going to talk about Surreal's Riot Engine. The two games we've shipped with this so far are very different in the way that they use the data. In Draken, we had very vast outdoor environments, and there was a lot of reusable resources, like you can see the trees here are reused. The terrain is unique. And then in Fellowship of the Ring, there's a lot of close-up detail, not as much vast environments, and we reuse things like characters and textures and stuff quite a bit. So this shows sort of the versatility of an I/O system like this. So it was first introduced in our engine when we did Draken for PS2. The first Draken was done on the PC, and we had a 10x increase in the amount of data just going to PS2. Just as an example, the main character in Draken 1 was, the main character in Draken for PS2 was 2,000 polygons, which was the same poly count as was an entire scene in the first game. So to fit that data into the PS2, which has the same memory limit as we had on the PC, we had to come up with a good solution to fit all that in. The engine was 4 years old when we added it, so it had a lot of development onto it, and so that's why I think it's interesting to get into the issues we had with integrating it into an existing engine. And then instead of being one continuous world, the levels were quite large. There were separate levels, and then there was a load time in between each one. But there was 2 to 4 hours of gameplay in each level. So, and almost 300 megabytes of data, of unique data, was streamed through the level for each level on average. So they were quite vast. We also used it on PC and PS2, Lord of the Rings, Fellowship of the Ring, which was a project we took on as a port of the Xbox version that WXP started. We used we used most of their art content and had used our own engine. We're also shipping 2 additional titles this year on 4 platforms: GameCube, Xbox, PC, and PS2. So that also shows that the system can be used on a lot of different platforms. So this is a shot of our level editor. This is one window in it, the window we use for data browsing and management. It's very important that when you have a lot of data, that you can organize it in a way that the designers and artists can get at very easily. And you notice the tabs at the bottom. Those are all resources that we stream in, and designers can add the data in the same way for each of the tabs. So, like I was implying before, the Riot Engine does deal with each resource uniquely and using a common interface. Each resource in the game is identified by its type, which is equivalent to one of those tabs, so textures, models, sounds, and so on. Animations are all, that would be the type. And by an ID, which is just a 32-bit identifier that is global to the entire game. So you can identify any resource just by a type and ID, and that gives you, 2 to the power of 32 possible textures, possible models, so on, which is a lot. So in terms of code, we implement each resource with its own class that derives off of a base class that allows the common code for managing the resources and streaming and loading and all that to be shared by all the different resources. And then each data type, so texture or so on, has its own cache, so we keep each one independently and manage it. And each resource has an H stamp on it so that the cache can determine when to flush the old data when it's full, and it does that with just a simple least recently used method. The cache actually increments the age counter every time a new resource is accessed, or just any resource is accessed. And then whenever you retrieve something from the cache, it then stamps that counter onto the resource. so that when it is flushed, it can easily tell which ones are the oldest. Or sorry, when the cache is full, it can easily tell which resources are the oldest and can remove those from the cache. And then very important, since all of our data internally, even at runtime, is referenced by ID, you have to be able to look these up really fast. And we use a hash table for that. And the good thing is generally you know ahead of time what type of data you're looking for. The renderer knows that it wants to get a model or it wants to get a texture. So all you need is the ID. You go right to the model cache, say, give me that texture, and boom, there it is. So how does the loading work? Well, when you go to retrieve a resource from the cache, if it's there, it just returns the resource right away. If it's not in memory, then it has to load it, and that process is initiated by just creating a new one. So it just calls, for all intents and purposes, new, texture. And then each resource has a state, and when you first retrieve a resource and it's not loaded yet, it immediately sets the state to pending. That just means the thing isn't valid. And then it returns it to the caller. So the first time you grab a resource, if it isn't in memory, it's always going to be pending, meaning the data is not ready to use, and the caller has to handle that appropriately. Then the cache calls the virtual member load of the resource, which builds data requests. And there can be any number from 1 to 20 for the data that it wants to be loaded off the DVD. And then the requests are queued up by some low-level loading system, and then processed in a separate thread, or in the case of PS2, on the IOP. Once the load completes, it's finished loading up the DVD, it calls a series of callbacks for each data request that are members of the resource class, and that can validate or invalidate the state of the resource. Now, valid just means, okay, all of the data that I requested is loaded, and you can go ahead and use me. And invalid means that either the important data requests that I made aren't loaded or aren't on the DVD at all. And valid things just stay in the cache and are flushed in the same way as anything else. But if something's invalid, generally nobody will be using it because it's bad. When the game ships, there's never any invalid resources, so it's really just an intermittent development thing. So in order to determine, or in order to effectively cache these things, we need to keep a reference count on them to determine whether they're being used or not. You never want to flush a resource if somebody's using it. So each resource maintains a reference count, and this works very similarly to probably what everyone's used to in COM or any DirectX API, where you retrieve an interface or in this case a resource, and you release it when you're finished using it. So the cache will never flush a resource unless the reference count is 0. And so if anybody's using it or captures it, the reference count will always be non-zero. It also allows multiple pieces of code to access the same resource at the same time. Just an important side note, if multiple threads are going to be accessing these things, all of these things like reference counts and all of the cache functions need to be thread protected. So the renderer also needs to hold reference counts on the resources that it's using, and then sort of release them at the end of the frame when you're done. A lot of times you want to store things like vertex buffers or DMA vertices off to the graphics hardware, and the renderer needs to keep a reference on those things so that they don't get freed by the cache. Now, since the loading happens in a separate thread, or the queue is processed in a separate thread, that is the thread that determines when the cache gets full and will flush things in that separate thread. So that means if you're in the main thread and you don't have a reference count on something or a reference on a resource, the other thread can come in at any time and flush that thing. So you can never rely on the data being there at all unless you have a reference count. And then we do have a method for locking resources in the cache. It's just a flag. You want to do that for things like player animations and stuff that you just don't want to be flushed. Because even if I have an animation that I don't use for a really long time, like some attack or something, when the player hits that button to attack, that animation has to play right there. You cannot have any delay at all. So this is some code of just a really simple example of an in-game overlay, in this case a health meter. So usually what would happen is the resources are identified by an ID, and the ID usually comes from a parameter from like a data-driven system or something like that. And the first thing you can see here is that we're going to define a smart pointer class, and this is a class that kind of wraps all the functionality of handling the reference counting. When I call into the texture cache to get a texture, that texture resource will immediately have a reference count taken on it so that it can be used without being flushed. The smart pointer's job then is to maintain the reference count, and anytime I reassign the pointer to the resource or anything like that, it will properly pass on or add references as needed. And then here's the very important check that you now have to do to the data. You can't just start using it right away. You have to check and make sure that it's actually valid. So if it's pending or invalid, you don't want to use it. Now there's two exit points to this function right here and here. When this class goes out of scope, of course, the destructor will be called. The destructor will release the reference on the resource. So both here and here, the resource will be, or the reference count will be decremented and indicating that it's no longer used. And then here is where it actually draws it, and it passes the texture onto a draw function to draw up on the screen. And then when it's done drawing, it can go ahead and just return and indicates that this function itself is done with that texture. Now the draw function may pass the texture on to the renderer, and then the renderer may take a reference on it. And then, so it's really, you just localize where you want to establish references and usages. One other important note is that you don't really have to ever check for null on the pointers. The cache will always return a valid texture, as I was showing before, where it would call new on even if it doesn't exist in the cache, it would create one for you. So let me talk a little bit about the specifics of the several platform architectures that we did in our engine. The Xbox PC has a thread-protected queue. The main thread queues up the resource requests in, and then the queue will wake up when something. Sorry, the loading thread will wake up when something is queued and initiate calls to the hard drive or the DVD to load the data. And then the thread will sleep while the data is loading, allowing the main thread to run. In PS2, it gets a little more complicated, but has some advantages in that you can build your own custom program that you can put on IOP that can do a lot of interesting things that you might have a less advantage of putting it on the main CPU, because the second thread, of course, is going to take time slices away from the main thread. So again, there's a queue, lots of DMAing of packets around, of data around, because there's potential for things like sounds and stuff to be loaded into SPU memory directly instead of going through system memory. All the I/O on the PS2 goes into IOP memory directly, so that has a good advantage in that you can keep sounds and things out of main memory, and the main CPU never has to deal with that memory. The data requests are queued up on IOP using the CIF RPC API, which is the remote procedure call system. The IOP also maintains the directory structures of the database lookup tables that determine where the data that it needs to load is available, or it's where it sits in terms of what sector and so on. So I really wanted to share some other implementations of streaming systems, and there's a lot of games that use these kinds of systems. And I actually did talk to a couple other developers besides the Getaway or besides Sony Europe and Naughty Dog, and they, needless to say, they're very popular games, or I guess, and they asked me not to say the name of the game, but let me just say that it's very similar to these implementations in some of the other developers that I've talked to. The interesting thing about Getaway, you'll notice by the screenshots, is that they're very, it looks very photorealistic, so there's a lot of unique textures and stuff. They actually went around London and took pictures to get all the textures. They're recreating 46 square kilometers of London. It's almost 2 gigabytes of data. And they break up the areas into small squares. They're approximately 250 meters in squared size, and they're sort of stitched together in a custom tool. So they have to be pre-processed before they can be used in the game. The tool groups together the chunks based on the visibility information, and these chunks are then what it loads instead of individual resources. The tool also does, optimizing and tri-stripping, things like that, and the artists can have some control on how the grouping is done to sort of suit the data that they build. So this is a screenshot of their custom tool. One of the very important things, I can't emphasize this enough about doing kind of a streaming system, is to have some kind of profiling or analysis tool so that you can look at how your data is laid out or distributed, or how the data is being used by the engine. In this case, this shows all of the specific points in which the data resides, the different draw groups, and the red and yellow areas are the ones that are most dense or most complex, and the least complex areas are farther out in the boundary. So this determines the amount of activity that's going to be going on in terms of I/O when you're in those areas. And then this is another visualization of the drawing groups and their interconnections in terms of visibility and so on. So one interesting difference between the Getaway and Surreal's engine is that the resources are handled very differently. The big advantage to that is that you can group them together and load them in big chunks instead of individually. The animations are all loaded at the start, and high-level visibility information is also loaded. That's just resident throughout the whole process. The unique world data streams into 8 half-meg chunks, so it's a total of 4 megs allocated to the unique world data. And then, in addition, each of those chunks has low detail textures that it can fall back on if the higher detailed ones aren't loaded. So for textures, it streams them into smaller shareable chunks that can be reused throughout the game. And other low priority resources are handled differently as well. Characters, cars, music, and dialogue have a similar streaming sort of caching system. So in addition, I'd like to talk about Jak and Daxter. The really amazing thing about this game is the amount of unique content that you see in the game. Every rock and object in the game seems to be built completely uniquely. And a lot of that has to do with the fact, actually, the architecture that it's built on. So practically everything is streamed in this game is really built from the ground up to be a streaming system, including the game code. A lot of their code or most of their code is written in a language they call Goal, which is very Lisp-like, and it maintains it knows about all the data that's being accessed and used within the code, so it can really manage that, and it's ideal for kind of a streaming system. So there's a lot of resident data including the kernel that runs the thing, player geometry and animations and things like that are used throughout the game. Common objects like crates and sounds and textures are all resident the whole time. And then in terms of the dynamic data, you've got up to 2 levels loaded at any one time. So this is very similar to the track example I gave. The key is that any one area that you're in can never see any other area that a connected area may also be connected to. So it's exactly like the track example I gave you. So generally, the two levels that are in memory are the level that the player is currently in and the one that the player is approaching. So each of those two level buffers contains all the data that's required for that area, except sort of dynamic data, things like cutscenes, streamed audio, and animations that may be used intermittently. And those are cached. So the advantage of doing this, of course, is that you can read the level information and the data used for that level in one large read operation. So you don't have to do a lot of seeking because you can just initiate a big load. The one thing that you need to do if you do that is be able to abandon the loading. The player may walk towards one level, you initiate the loading of that level, and then the player decides to go the other direction toward the second level. And that means you need to abandon the loading of the one you were loading because the player's now going the other direction. And I think I know the PS2 is able to do that. I'm not sure about the other systems, but so if you start to integrate a system like this from the information that I've already given you, you'll probably run into a lot of problems and go crazy and start building Lord of the Rings characters out of marshmallow Easter peeps, like this individual. Sorry about that. Laugh upward. So prefetching requires you to, or is a system where you can preload the data that you're going to be needing, and that depends a lot on how you handle the resources and or handle when the resources aren't available and when the data is not there. One way to handle that is to not display the data or not play it until it's valid. And if you do that, of course, you're going to see glitches in the game. You're going to see problems, and prefetching the data will solve that. Another possibility is to use low detail information as a fallback, like the Getaway does that for their textures. And you can also do that with sounds, like load the first, or have the first half second of all the sounds that you're going to be using in memory already, so that you can start playing them, and if they're not loaded yet, and then load the remaining part of the sound as needed. But any kind of a solution like this, in terms of handling the data when it's not there, really doesn't work, because you see these problems in the game, and the player's just not going to think that's cool. So a lot of resources, really need to be made available immediately. Impact sounds and player animations need to be there immediately. You cannot have any glitches or problems with those, or sounds playing late. You hit somebody and then a second later you hear the sound. That just is not a commercial quality game. Another big problem is spawn objects or special effects. If you have an explosion or something, the textures that are going to be used in that explosion need to be there. So prefetching or preloading those textures when a missile flies through the air, for example, or locking them in the cache is really the only solution for that. So there's many techniques for prefetching. Ideally, the prefetching that happens in the game should be as automated as possible. So using things like the visibility and layout information will tell you, what's coming up, what's around the corner, so on, and that can be loaded ahead of time. Also putting specialized game code in there. A good example is like a chair that the player is going to shoot and it's going to blow up. Well, when the player comes near that chair, the chair can make sure that the pieces that are going to fly out are loaded and ready to go. And then if automated things don't work, you can always place triggers, have the designers place the triggers to prefetch things that they know are coming up. You can also set priorities on the resources to say, well, these walls and this floor are much higher priority than this mug or jelly donut that's sitting on the table over there. And then if any of those fail, you can always use a gimmick. There's really been some good ones like Metroid Prime. It's a great example. It has doors in between its areas, and if you shoot them, every once in a while the door won't open right away, and that's because the next area hasn't been loaded yet. And then some games will fade to black if the data is detected that, oh, there's way too much stuff loading. I know that I'm going to get some fading or popping in, so I need to fade to black and do a little load thing or something like that. That's, I believe, what Grand Theft Auto does when you're crossing the bridge between towns. If you notice, a lot of times there'll be a lot of dropout, and then it'll bring up a, hey, welcome to Vice City. So that's kind of hiding the fact that it needs to load the data. And then Jak and Daxter did a great solution, which is you just make the player trip and fall and stop them from progressing. So a little bit about DVD performance. Everyone, I'm sure, knows that seeking is bad. Maybe you don't know how bad it is. From one end of the DVD to the other, it's almost a second delay. Even if you read the same, if I read a chunk of data and then read the next chunk of data, just initiating two read operations like that will give me pretty much a minimum of 20 to 30 second hit on the PS2. But DVDs are very fast at streaming. 4 to 6 megabytes a second is pretty typical for the PS2. So you really want to group them together into big, large chunks and read them all at once if you can, instead of initiating a lot of different reads. So Getaway, when they first implemented their DVD loading system, spent 70% of the DVD time doing the seeking. And once they optimized it and to load it into bigger chunks, they were able to reduce that to only 20%. That means that 80% of the time was then spent at loading real data. One way to create linear chunks, and this is what the implementation in the original implementation in Draken does, is it actually reorders requests at runtime in order to make them most optimal. I'll show you that in a second. And then a very important thing as well is to generate statistics, or you can log how the data is accessed in the game, and then use that to reorder your data on the DVD itself. So, quick example of how that would look. If the resources are just laid out randomly, then the access again is random, and you would get the DVD read head sort of jumping around like that in time. That seek time then contributes a lot to the amount of time that it would take to load each resource. So if I were able to reorder the requests such that they were in proper sector order, and I reduced the seek time, then I reduced the load time. And then most optimal, of course, would be to group those together and read them all at once. So memory layout, if I was to just call new on every resource individually, I'd end up with a memory map sort of like that. The gray represents the rest of your engine and game data that's sort of distributed throughout a memory pool. When I start out the system, I'd end up with something like this, where I have all my memory allocated, and then I have a big block of free memory at the end. So if I want to allocate a big, say 64K chunk or something, I can just allocate that linear block at the end of memory. Now after I play a while, though, all of the textures, geometries, and animation are resources that are dynamic. They're being loaded in and flushed and so on. And whenever you have large blocks of data that are dynamic like that, after you play a while, you're going to end up with really bad fragmentation. So you notice I'm not able to allocate any large linear chunks out of that memory map on the right. So one way is to isolate your dynamic data into separate memory areas. And although you may get fragmentation within those blocks, you won't fragment your entire memory map as much. So avoiding fragmentation, making sure that using blocks that don't move is the best way. Isolating them, again, like I said in the previous slide, is a great way. Using resources like textures that are similar in size. If you have a 128 by 120 texture that can be reused in the same memory. Custom memory allocators do work, separating out blocks of memory so that common sizes are together. Works well. Fixed memory pools, very important. And garbage collection is also possible and works well when you do reference counting or scripting where you know where all the data is and whether it's being used or not. And you can move it around when it's not. The problem with that is that moving memory around on a lot of consoles can be rather expensive use of time unless there's some DMA system. So I like to give you a little demo of Draken, and keep in mind this was a Generation 1 engine that used our engine. What I want to show you is some debugging stuff. Up in the upper right-hand corner is all our sort of runtime statistics. And you can see that the last line there, IOP, has a little letter that will show if I start flying. It'll show me what's loading. T is texture, M is a model, S is a sound, so on. So let me make myself invincible. And you can hear the DVD going over here. And one thing that's interesting about this is that there's a menu here where I can debug the memory use, and it shows me the cache sizes, how much memory is being used for each cache, and so on. And I can go in and I can actually flush the cache. And you can see the game's still running, and the data is loading in off the cache, but everything still works. So the engine completely handles the data not being there without crashing. Now that would normally never happen during runtime, but you can see how much of the data is dynamic and loadable. So I'd really like to thank Daniel Navarro from Sony Europe for his help on the Getaway, and Stephen White for great information on Jak and Daxter. So are there any questions? Yeah. Right. So I think the question was, in the case of Draken, where the levels were granular. Yeah, in Fellowship, the levels were actually smaller, and so the load times were decreased between each one. The engine doesn't necessarily require granularity. That was the way the designers built it. I mean, you could have one very large level, and that would be the entire game. So they broke it up like that just because we didn't really have tools for stitching together the levels. So they would build them individually and then load. What was the second part? Right. Well, yeah. You need some kind of fundamental layout information, so connectivity information, whether it be a scene graph, which is what we use, has references to the individual models that may be used in those areas, and then from there, again, there's a dependency of models referencing textures and so on. In terms of Draken, like transitioning between levels were initiated by little triggers the designers would place that would say to load the next, essentially, scene graph for the next area. Generally, there would be some kind of a load bar or a black screen when you go between areas. Yeah. No, they would just say load this next area that would be identified by a level or a scene graph, and then that would know what to load. Yes.
You mentioned priorities. I wonder, what do you assign priorities to requests, screens? How do you handle them?
Well, in the Riot engine, whenever we make a data request, we prioritize it with sort of a minimum latency that can be that we can wait for, and then the IOP will then reorder the data based on those latencies. So if the time when the data was originally requested, in other words, when I make a data request, it would say I need this within 2 seconds, and if the data at the time when the queue is processing the data approaches that time when the minimum time when that data was required, then it will put that ahead of the queue and load that first instead. So that's how the prioritization works. We use the latency and a priority. Latency just kind of says I need this right away. The priority says if I've got a bunch of things that all have the same latency, then pick one over the other. Yes. Yeah, most of that work we've done more recently, just because as your data increases, you want to reduce your seek time even more. So we've been generating logs and doing statistical usage things to determine how to place those on the disk more efficiently, so that data that is used by one level is all in the same area. And we haven't done this yet, but we also want to repeat data on the disk as well. Yeah. Yeah, lots of level of detail was the question. Did we do any level of detail? We have several. We have model level of detail, where like if something's far away, we just load a low detail version of it. We don't have to load the high version, although the high version is prefetched. Also, we use distance culling a lot. So if it's a small object, it'll just fade out. If an object is distance culled, it has that information ahead of time, so it doesn't need to know. It doesn't need the model in order to determine whether to even render the thing or not. So if it's too far away, it won't even load it. And actually, interesting side note on that is the Riot engine will actually fade in models that when they load. So if things are loading in on the horizon as the player moves toward the horizon, the fade in sort of simulates the fog, so you don't really notice it. Yes? The question was, do we, in terms of creating texture surfaces for textures in like DirectX on the PC, what we would do is allocate a DirectX surface, and then the loader would load the data directly into that, and then that would be used by the renderer. Does that answer your question?
That was my first question. Because I've actually been quite good at this.
Mm-hmm.
I've run into monitor what you might call driver blocking techniques, where you can always run through it every now and then. The driver seems to have a little bit of conflict when things being rendered and looks like it's being loaded. When you make calls like blocking the surface driver to fill it up, the drawing kind of gets called for very tiny, small amounts of time. I was wondering if you guys have actually seen those kind of things.
No, we haven't noticed anything like that. Anytime you fill a surface, it'll always be a new surface, so that may be the reason, is that it allocates a new DirectX surface. You don't really have to worry too much about fragmentation issues and dynamic memory as much on Windows, since it's a virtual memory system. But yeah, in the back. Internal. So the question is, in our engine, we have every piece of data separate, and the answer is, in memory, yes, it's a separate class, but it's loaded together in big clusters. So the loading time is ready, and once it's brought into memory, then the individual resources can be accessed independently. No, well, each one is maintained in a separate spot in memory together, so the textures and the models and so on are maintained together. On disk, are they together? In the original Draken implementation, they were, but we want to, ideally, they would be distributed throughout your database in the order that's optimal for the level. And again, that gets back to the statistics and organizing it in the optimal order. Yeah. I'm sorry, can you speak up? Ordered on the DVD, you mean? Well, that could get into a whole other thing. That's some stuff that we're just starting right now. So, but it involves having a system for logging the information as the player plays, and also for loading when you initially load the level, because you can improve the initial load time. So just generating a log of where and what size the accesses were, how long they took, and so on. And then what you do just for loading, as an example, it's really simple. You just order it in the same order that it wants to load it in every time. In terms of dynamic play, what you have to do is assign a relationship or a weight between each resource, and then use that to determine the best order. Yeah.
Do you ever run into any problems with circular references?
You can't really get that problem because, like, for example, if I can't really think of an example of where. I mean, because you never really have a model reference a texture and then a texture reference a model, so it's more of a tree instead of a graph. But even if you did have circular references, eventually the data would get loaded, even if the main thread that's accessed. I mean, I could sit there in a loop and do nothing, and the data would still be loading in. So once the request has been made, once the data does arrive, then you can continue using the data. So even in a circular reference case, eventually one part of that reference is going to be available, and then the whole thing will end. Oh, you mean like, okay. So you mean like if I have if a data gets flushed and then I reuse it again at another point in the frame, is that what you mean?
No, I mean, say you had two objects in your database that refer to the first
Okay.
They stop being used. Normally with your system, you flush things once they don't have any positive ref counts in your smartphone.
Mm-hmm.
But if they do reference each other, they always have positive ref counts.
Well, yeah, a resource will never take a permanent reference on another resource. So it's usually the client code that uses it. So, okay. I think we need to cut it off. So, thank you, everyone.